So I think the last time we looked at a decoder, right? And I showed you guys how to draw the decoder's internal architecture, right? Using AND gates and then NOT gates and stuff like that. Using AND gates, NOT gates and stuff like that. So our next one is the multiplexer, right? Who knows what a multiplexer is? Multiplexer. You guys have heard of it before, I'm sure. What is it? So it's just the opposite of the decoder we did, right? You saw that the decoder did what? We had multiple outputs, right? And then it selects just one of the outputs, right? So here we are dealing with a multiplexer, and then it's like if you have so what? Right? So it's like this. If you have, let's say, a road, right? And then you have multiple cars coming to that road, right? Only one car can pass through this road, right? So you need a way of selecting which car goes through the road, right? That is the purpose of a multiplexer. As simple as that, right? Multiple inputs, then only one input is routed to the output, right? So we are going to see how to draw the internal architecture of a multiplexer, just like how you saw how to draw the internal architecture of the decoder, right? And this is the truth table of the multiplexer. And then from the truth table, you can always draw the internal architecture of the multiplexer or any other circuit, right? So the symbol for the symbol for the multiplexer is that one over there on your right, right? So what this just means is that we have two inputs, right? D0 and D1. We have a single output, Y, right? But how do we select which one to go through? D0 or D1? How do we select it? We have a very important signal known as the select signal, right? So that is what is used to select whether D0 is routed or D1 is routed, right? Master, I'm waiting for you. My wife, as I did that. What is your this number? Okay, so as I said, one signal is routed through using the select signal, right? But the most important thing is that you must know the number of bits of the select signal. Very, very important, right? So if you have two inputs, just two inputs, like D0 and D1, right? the number of bits that S will be is just one bit, right? One will be 0, and then the other will be what? 1, right? So if S is 0, you will route D0 to Y, right? If S is 1, you will route D1 to what? 1, right? So in case I have 4 inputs, right? D0, D1, D2, D3, right? What will be the number of bits to for S? 2 bits, right? So 0, 0, 0, 1, 1, 0, and 1, 1. Very easy, right? So now let's study the truth table over here. Right? What do you think is happening? When S is 0, what happens to the output? Look at the truth table. That's what you'll be using. And then everything I say here is coming in there. So I think I've already said the exam. So everything I say is in the exam. So if you don't see it, I didn't tell you. Right? So let's study the truth table. This is the select signal, the S here, right? The S is used to route one of these signals. And I said if S is 0, you route D0. If S is 1, you route D1, right? So what do you think is happening here? If S is 0, what happens? What is the output? Ah, just 0. Steady, steady. If S is 0, so if S is 0, what happens to the output? Look on the phone. If S is 0, what happens to the output? Look at it very well. There's a pattern. There's always a pattern in digital system, always a pattern. And then there's always a kind of relationship between the inputs and then the output. Right? So when S is 0, what happens to the output? You see that the output is what? 0, 1, 0, 1, right? What is 0, 1, 0, 1? D0. Have you seen it? So 0, 1, 0, 1. If S is 1, what happens? You see that the output is 0, 0, 1, 1. And then D1 is what? 0, 0, 1, 1. So it means that when S is 0, we route D0 to Y. If S is 1, we route D1 to. That's easy as that. Right? So how do we draw this? How do we draw the internal architecture using this truth table here? Just like how we did for the decoder, right? Who can draw the internal architecture of a multiplexer using AND gate, OR gate, or XOR gate and stuff like that? Who can draw it? Just like how we did for the decoder last week, right? Or last week. How do we go about drawing the truth table? Who knows? Who knows? Nobody. Okay, so how did we even go about it? So first of all, which gate did we use? So let's see. Let's try an AND gate, right? We are using the truth table, so let's try an AND gate first. And then you can see that we have one output, right? And two inputs. Yeah, three inputs. So now let's do for D0, right? So if I use an AND gate, right, must have an output and then an AND gate, a two input AND gate has two inputs. Right? One of the inputs should be S. So when S is 0, one of the inputs should be X, right? And then one of the inputs should be let's do for D0. So when S is 0, right, we route D0 through to the output, right? Right? Yes. So in case I use an AND gate, right? For an AND gate, when one of the inputs is a 1, the output depends on the other. You know that? So because S is 0, I can just come and invert this one here. And what has happened? So if S is 0, here becomes what? 1. And then because here is 1, the output is directly this one, this 0. Right? Are you seeing it? Very, very simple logic and stuff like that. So if S is 0, this 0 gets inverted, it becomes 1. The output of the AND gate depends on this 0. So if this 0 is 1, it becomes 1. If this 0 is 0, it becomes 0. So we say that the output is this 0. Right? That is just for this 0. Now, we can use another AND gate again. So here we have D1. But for D1, S must be what? 1. Pay attention. S is 1, right? So when S is 1 here, we don't use any not gate anymore. Just directly. So when S is 1 here, D1 will get routed. Right? So here is Y, here is Y. But we can't have two Y's, right? Y is just one output. So how do we combine these two to become one? Who knows? Which gate are you going to use? Now, we have done for D0, D1, S, and then for S, right? Now we need the output to be just one. But here we have two outputs, this one and this one. How do we combine the two to become one output? What gate do we use? So we have two outputs, right? But from the table, we have to be just one. Why? We want to combine this one and this one to make it one output. I can't just do this. Is this possible? So if I do this, what do you think happens? If here is 1 and here is 0, what is the output? 1. So what you do is you use an OR gate, right? And then you get your what? Very good. Why are we using an OR gate?
Because that side is zero and the other side is one.
Mhm.
So when you use the G zero added, you get a one after you get it.
Mhm.
Over here you get a zero.
Mhm.
Zero and one. And all meaning you have zero or one. The output is that's
The most important thing is that for an AND gate, right? When one of the inputs is 1, right? The output depends on the other input. But for an OR gate, right? When one of the inputs is 0, the output depends on the other gate, the other input, right? So, for instance, we cannot use an AND gate here. It will be impossible. So, if you use an OR gate here, and then let's say now here, I can come and combine because this is S and this is also S, right? I can combine the two like this, right? Have you seen it? So we have S here. So if S is 0, what do you think happens? Here becomes 1. Here becomes what? This, this 0. So because here is 1, this 0 will come here. Right? If S is 0 here, here becomes 0. Automatically for an AND gate, once one of the inputs is 0, the output is what? Is 0. So if here is 0, for an OR gate, as I said, once one of the inputs is a 0, the output is directly the other input. So here will become 0. See here that. You can go divide for the 1 for if S is 1. So this is the internal architecture of a multiplexer. Using only AND gates and then OR gates and NOT gates. Easy, right?
Yeah.
Now our next component is a comparator. You guys know what a comparator is? A comparator. So what is a comparator? So a comparator is simply an equality checker, right? So let's say I have two inputs. I have only two inputs, input A and B, and I want to check if A is equal to B. Right? So all I need is a comparator here. A comes in, A comes in, and then we have our output, right? So for the comparator, if A and B are the same, what happens to the output? If A is equal to B, what is the output? I mean, you guys write your code, you guys write codes all the time, and then you do this all the time. So if A is equal to B, what happens to the output? What is the output? 1 or 0? 1. If A is not equal to B, what happens to the output? 0. Right, so I can easily draw my truth table as A, B, and then my Y, the output, right? Are you paying attention? Don't go and get confused in the exam if I just waste something small. Right? I know. So here we have 0, 0, 1, 1, right? We have 0, 1, 0, 1. Alright. So if let's pay attention here. So for the truth table, if A is 0 and B is 0, what is Y? 0, 1. 1? 1, 1. Right? As easy as that. So this is the truth table of a comparator. We compare A and B, and if they are the same, the output is a 1. If they are not the same, the output is a 0. As easy as that. So how do I draw? Which gate do I use to achieve this one? So now we are not going into the internal architecture. What gate can I use to construct this? You raise your hand, right? What? Not. Not gate. So the not gate has only one input. Only one input. So you cannot have A and B. Only A. And then it gets inverse. So it's not the not gate. Yeah. Which gate can I use? Exclusive. X, pay attention. X 4 gauge, right? So let's check. So let's see the truth table for our X4 gate. So let's say here's X4. So for X4, right? If A is 0 and B is 0, what is the output? X4 gate. Ah, 0. If A is 0 and B is 1, 1 0. 1 1. Great. So you see that the X4 gate and then the Y output here is directly opposite. So what do you do here? Not XOR. So if I invert this, if I invert this, right, I get what? 1 0 0. That is equal to 1. So it's a Something like this. Okay. Have you seen it before? Yes. So this is A, this is B, and then you have your right here. As easy as that, right? Okay, so now if I have four of them, so if A is 4 bits, right, and B is 4 bits, how do I draw the circuit? This one is just for 1 bit, right? 1 bit, 1 bit. So what if A is 4 bits and B is 4 bits? Hmm? Draw it, draw it. Draw it and let me see something. So now we have 4 bits instead of 1 bit. So I mean that's how the exam is going to look at. I will just give you some 1 bit. So it will be more complex than that.
Say, don't do that. If I do that, we are watching you.
Are you done? 4 bit, 4 bit, 4 bit. A is 4 bit, B is 4 bit. So how do I compare them? What is this? How do I combine the base to achieve a 4 bit? You know that it's 4 bit, 4 bit, but the output is just 1 bit. You know that. So we have something like the truth table will be like A, B. A will be 4 bits, so probably A3, A2, A1, A0. And then we have B3, B1, B2, B1, B0. And then you have an output to a Y. Something like that. I said we did for only 1 bit, A and B. If you have 4 bits, A is 4 bits, B is 4 bits, so it means that it will be A3, A1, A2, A0. B3, B1, B2, B0. Understood? So what you are doing is you have to compare because you want to compare if A is equal to B, right? So you have to compare A3 and what? B3. Compare A2 and what? B2. Compare A1 and B1. Then compare A0 and B0. As easy as that. Yeah, you combine all the outputs. Then you have your so it means that how many not XOR gate what is how many gates do I need? Okay. So if all the outputs, let's assume you have the outputs, all the outputs are coming. So what gate do I use to combine all of them? What gate do I use to combine all of them? And gate. So if you use four of these ones, right? For A3, A2, and whatever. And then once you get to output, you use an AND gate to combine all the outputs. And then you get your one output. It's as easy as that. Right? So if I bring something like that, in case I bring something like that, you guys can easily. So here, what that means is that, as I said, we compare if. So pay attention. In case the number is, let's say, in case the number, we have the number A and B. If A is, let's say, 0011, right? And B is 1000, right? What you do first is you compare this and this. That will be the first one, right? As soon as you compare that one, what happens to the output? So if A is 0, if one of the A's is 0, if A3 is 0, right? And B3 is 0, from the truth table, what happens? The output is what? Which one? If A is 0, right? And then the output is 0, what happens to the what do you call it? The output of the first NOR gate, X NOR gate. And then if A2, so now go, so if A2 is 0, and then if, and then B2 is 0, what happens? can use it. If A is 0, A3 is 0, B3 is 0, what happens to the output? If A, so now, so now we have A3 being 0, B3 being 1. What is the output? Here is 0, here is 1. What happens to the output? 0. So if A 0 1 becomes, here becomes what? 0. Automatically, you don't even care about this anymore. The output is 0. Even if one of the bits is 0. If one of the bits is different. So now, this is the assignment I gave you guys, right? And okay, you bring the assignment. Yes, before I solve it. I gave you some assignment and I said bring it today, right? Hurry up, pass it forward, pass it forward. Why are you looking at me like that? Hurry up, hurry up. Is that all? It means that somebody is not doing it, right? Is that all? Okay, so now our next component is an ALU, right? So now we know how to use logic gates to make a thing like encoder, a multiplexer, and stuff like that. So we are going to use that same idea to design what is known as an ALU, right? And from the assignment I gave, what did I give you? I said you have a very simple two inputs ALU, right? Very, very simple. Two inputs, one output. A, B, or Y, right? And then I gave you the truth table. I said if A, no, and then we have some, I think F, that's the first one. So if F is 0, 0, what is the output? What did I give you, sir? Wrong, 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 wrong. So if A is 0, 0, if F is 0, 0, right? If F is 0, 0, we have an AND gate. If F is 0, 1, we have what? If F is 1, 0, we have XOR gate. And if F is 1, 1, we have the not of B. Right? So what? So here, all we are doing is that we have our selection selection now is this zero. Our selection now is just simply F, right? So we have multiple outputs. We need only one. We have multiple inputs. We need only one output. So all you have to use is a what? What am I going to use? A multiplexer, because we have multiple inputs and then we need to have only one output, right? So my first one is 0 0, second is 0 1, 1 0 1 1. And if we have 0 0, we have an AND gate, right? So all I have is an AND gate here, A, B. Simple. The next is I think an OR gate, A, B, XOR gate or something like that. And then the last one is not B, not gate and then B. Then you have your 5 marks. Somebody did it. Would somebody to have done it? Wrong, wrong. So, I can see the pattern. So the first is like the same thing. So I'll give one of them the full mark and then the other, and I get toss a coin.
I'm meeting God.
Okay, and I'll meet you there also.
No problem.
Okay, so our next gate is known as the tri-state buffer, a very, very important gate in digital circuits, right? So what I mean is that with all the gates, every gate as well in digital system, if you have an AND gate, right, there's always an output. Pay attention. There's always an output. Either the output is 0 or it's what? A 1. Always, every time there's an output. But there are times that you don't need an output or you want the output to float, right? You don't want your output to be 1 or 0, right? So that's when you use what is known as the tri-state buffer, right? So what happens is that in the tri-state buffer, all we are doing is it's a buffer and then with an enable signal, right? So when E is 0, you don't want the output to be a 1 or a 0. You want the output to float, not 1, not 0. So when E is 0, the output is Z. Z is known as floating or high impedance, right? Now when E is 1, that's when you allow your signal to pass through from the input to the output, right? So you see that when E is 1 here and then A is 0, the output is what? 0. When A is 1, the output is 1, right? Very, very important component in a digital system. And then what is it used for? What can I use this for? All right, so you know that within your CPU, within your CPU, right, you have only one bus. For those who know, you have only one bus, and then you have components connected to the bus, several components like your CPU, memory, and stuff like that, right? But the most important is that only one component is allowed to use the bus. Only one component is allowed to use the bus, not two. It's impossible for two components to use the bus. So you can use this tri-state buffer to design a thing like this. So now all you do is that if the CPU wants to use the bus, right, what should it do? It should just enable the gate there. You see the gate CPU. If CPU wants to use the bus, it just makes here 1, right? And whatever it has will come to the bus, right? If CPU makes here 0, nobody will come here, it will be floating, right? Now, if memory wants to use the bus, all it has to do is make here 1, and then whatever value is here comes to the bus. Very, very simple circuit for a shared bus. Are we there? Do you understand? Do you understand? Do you understand? As I said, if you don't ask anything, these are the things that are coming back a little bit twisted, right? All right. So our next thing is the same exact way. Okay. Now we know that within the CPU, right? You have your bus again. You have your shared bus. One bus, one bus. You have CPU. You have memory. You have I/O. All of them want to use the bus, right? So how do they use the bus? You guys might have stated this one somewhere, probably or not. So now we have CPU that is connected to the bus. We have memory connected to the bus. We have I/O connected to the bus. But how do they use the bus, right? What happens is that from CPU, right, there is a signal known as the request signal to the bus. Request, right? From CPU to the bus. And then there's also another signal from the memory to the bus, also known as the same request. Then from I/O we have the same request, right? Right? So if CPU wants to use the bus, all it has to do is it activates this line. So if I say activate, right, I say it means I just make it one. If CPU wants to use the bus, I want to request to use the bus, so I make this line one. Then it goes to the bus, and then the bus will know that CPU wants to use it. So what the bus does is that the bus will grant or deny, and then the bus will grant or deny based on another signal to the CPU, which is known as the grant line, right? So from the bus to the CPU, there's a grant line. From the bus to memory, there's a grant line, and then from the bus to I/O, there's also a grant line, right? So if CPU wants to use the bus, it activates or a request it makes here one, and once it goes through to the bus looks at it, and then the bus will grant it. And then if I say the bus was granted, it means that it has made this line one. If the bus denies it, it makes here what? Zero. Right? Are you getting it? Okay, so now what happens if CPU request, memory request, and I/O request at the same time? What happens? Which one will be granted? Hmm? They all requested at the exact same time. So they all made, so here request is one, here request is one, here request is one. Which one will be granted? The what? Hurry up. These are very, very simple concepts. What is the first one? Why? Is it because it's on top of the memory and then stuff like that? What if I change it? Okay, so what happens is that, right, even before all this, right, the bus assigns the one that has the highest what? Priority, right? So it assigns priority to each of the components attached to it. So it assigns CPU to be probably 3. It assigns, okay, this memory to be CPU to be 3, memory to be 2, and I/O to be 1. Right? So when they all request at the same time, it looks like the one with the highest priority, and it gives a bus, it grants it. It makes that line 1. And then all the others, all the grant lines will be 0. So until that particular device or whatever has used the bus, then it will give it to the next one with the highest priority. Right? So here it means that one component can actually hijack the bus and use it forever. Right? So how do we mitigate that? How do we navigate that? If we don't want to use this kind of system, but we want that. Um, of course, we still want that. We still assign priorities, but we don't want one of the. We don't want one. We don't want one of them to use it forever. How do we stop this? Uh, you na. So means that you don't want your partner to. How do you stop it? Fire, fire. I mean, there are several techniques, probably 20 of them or 30 or 40 techniques to stop this. Very, very easy. And then you can even think about your own techniques to even stop it. Let me hear just one and see how. What can I do? Yes, of course. You can time it, right? So you say that once you give access to one of the buses, one of the components, right? You just time it after probably 5 seconds. You take the bus from that component and give it to the next component. It's as easy as that, right? Okay, so now this is how the priority circuit works. So in the exact same way, from you have memory, CPU, how you write it. So the request lines are the A3, A2, A1, A0. Have you seen it? Pay attention to the table. The request line are A3, A2, A1, and A0. The ground lines are Y3, Y2, Y1, and Y0. Right? So when A3 requests, right, Y3 must be on or off based on its priority level, right? So from the table, which one do you think has the highest priority? Which one has the highest priority? A3, A2, A1, or A0? Pay attention to the table. Why? Which one has the highest priority? Which one, when it requests, right, it will be granted, no matter what. No matter the other inputs. Why? Why? Which one has the next priority? The next highest priority after you enter it? Then which one? Everyone, and then it goes on, right? So it's like from the table, you can see that as long as A3 is 0, the Y3, as long as A3 is 1, the Y3 is what? 1, right? Then the next one is A2, the next one is A1, then A0 has the lowest priority. So who can draw the truth table of this one? The circuit for this one using AND keys or O keys or whatever. First of all, if you can do that. So what we are studying is we are using logic gates to design these circuits, right? So I give you a truth table. I tell you that I want you to use logic gates to design or to draw the schematic of the truth table. That's what we are doing. You don't know what we're doing right now. So now, how do I use logic gates to draw this or to depict this truth table? From how we also study how we did the internal architecture of the decoder, right? Then we did the internal architecture of the multiplexer, right? Now we are at the priority stages, and then we have our truth table. So how do you go about drawing the truth table? Right? And the exams, it will be some way. go away, right? You know, I'm not a full-time staff, so I don't really care like that. I get to ask me, and then you can train me whatever you want. I don't care. I'm gone. Yes, that was it. But based on your what? Please, how do we draw the how do we draw use logic gates to draw this? So let's start. Which one has the highest priority? Once A3 is 1, what is the output? Once A3 is 1, what is the output? The output is 1. So here we have four outputs, right? Y3, Y2, Y1, and Y0, right? A3 is connected to what? Y3. So that's where we pay attention to. We have Y3 and A3, right? As long as A3 is 1, Y3 is 1. So we don't need any logic. We don't need any logic gate at all. Direct line to Y3. So here, if Y3 is 0, if A3 is 0, Y3 is what? If A3 is 1, Y3 is what? You are done with it. You are done. Then you have to with some one mark here. Easy, right? Now your next one, we go to your next one. Y what? 2. Right? But Y2 depends on A2. Only when A3 is what? 0. So I use an AND gate, route Y2 to A2, and then use a NOT gate here, and I'm done. So it means that when A3 here is 0, it's when here becomes 1, and then A2 will not go down. Easy, right? I mean, yes, simple logic. Do you understand? You understand? Now, our next one is Y1. Y1 depends directly on A what? On A1. But A3 must be 0, A2 must be 0 before Y1 can be what? 1. So what do? Another AND gate with not and another not here. Connected to A3 and A2, and then your A1 comes. Your last one is what? Y0. Right? Y0 depends directly on A0. Only when A3, A2, A1 are 0, 0, 0. So you have your AND gate with 3 knots. Right? Connected to whatever. Simple as that. I mean, these are just like simple thinking. But I mean that you can draw this one in several ways, but this is how I've chosen to draw it. So if I give you something like this and then somebody draws something that makes sense, then any question? Do you guys understand? Any question? All right.